Hey everyone! So today I'm just going to go over thin layer chromatography, and I'm going to break it down a little bit simpler than maybe how you've come across it before. So let's get started. So we're going to do thin layer chromatography. It's also known as TLC. So basically this method is used to separate compounds of varying polarities. So if you want to know if a compound is more polar or nonpolar than another, or what composition that a solution is made up of, we can use this method to do that. So here we have our adsorbent sheet. So we use like a little sheet or a piece of paper card, and on it there is an adsorbent. So this adsorbent could be polar or nonpolar. A lot of times silica is used, and silica is a very polar adsorbent. So what happens is we usually draw a line here, and we start and put drops of our solution. So let's say we have our solution, we put drops of it like this on that line. Then what we do next is we add a solvent to this silica adsorbent, and usually the solvent will be the opposite of your stationary phase. So in this case, if we had a silica adsorbent on this sheet, we would want to add a nonpolar solvent, which is the opposite of a polar silica adsorbent. So when we add our nonpolar mobile phase, so something that is an example of a nonpolar mobile phase would be something like hexane, and hexane is a very nonpolar molecule. So if we added hexane here, then it's going to bleed down the sheet, and what's going to happen is the molecules in your solution, they're going to come down with it, but not every molecule. So you'll maybe see a gradient that looks something like this. And what's going to happen is you can measure the distance between these dots, and that's going to be, well, the distance from the beginning. So then that will be your RF value. So if you were to measure the distance between this dot and this dot, that's going to be one of your RF values. So RF. And then you could also measure this. That's another RF value. So what are these different dots representing? So basically, how far that one of your dots gets down here, that's indicating a very nonpolar molecule in your solution. So your original solution is made up of all these different compounds. Each of these dots represents a different compound or component within your solution. So if one of your components made it all the way down here, that means that it traveled along with the hexane. The hexane is nonpolar. So since like dissolves like, if your component went all the way down here with the hexane, that's just telling us that this component is very nonpolar. Now, if it didn't go as far, and if it's maybe closer to the beginning line, like right here, we would see that this is not as nonpolar as this component. So this component would probably be more polar because it has more affinity for your stationary phase, which is silica. So I didn't write, so silica is polar. All right, so now that we've got that down, so going back to RF values, basically what we see here is if your stationary phase is polar, and if your mobile phase is nonpolar, then these situations are going to apply. So if you'll have a low RF value for more polar molecules in this case. Does that make sense? Because this means that these components aren't traveling down as fast as this component. So obviously that means that this is having more affinity for your polar silica gel, and that means that it's polar because polar wants to stay with polar. So a lower RF value would be polar in this case, and something that's traveled further down would obviously have a higher RF value, and a higher RF value is going to indicate something that's nonpolar. Now obviously this will be switched if your adsorbent or your stationary phase is nonpolar and your solvent was polar. So you got to make sure that you take care of that and remember that. And that's all I got for you guys today. Bye!